All right, happy Cinco de Mayo. We've got our physics review session today where we're going to be looking specifically at Hooke's law, matter and materials. So this is chapter 7, and we've got state what is meant by elastic potential energy. So if we start by thinking about sort of just potential energy in general, potential energy is energy due to position in a gravity field or the shape of something. And so elastic potential energy has to do with sort of the shape of an object, where we're storing energy inside of the object due to sort of some change in its shape. Energy stored in an object due to its shape. And so something like an elastic band, a rubber band, if we stretch it, then that energy that we spent, the work that we did in stretching the rubber band or the spring, has energy stored inside of that, known as elastic potential energy. So we'll see if that language there is enough of the key language to earn the 1 mark here. Let's remember to check the mark scheme at the end of all of this. Sometimes we forget to do that. All right, it says a spring is extended by applying a force. The variation with extension x of the force F is shown in figure 4.1 for the range of values of x from 20 centimeters to 40 centimeters. So note that it's already giving you the extension. Sometimes they'll have the length, the total length of the band or the spring given, and you have to sort of calculate what the extension is. And so here, note that we're plotting extension against force. It says use data from the figure to show that the spring obeys Hooke's law for this range of extensions. And so we can really just look at this and see that it obeys Hooke's law, because Hooke's law says that, you know, these two quantities are going to be in proportion to each other, that the extension of a spring is, you know, going to be in proportion to the force applied to it or the compression. And we can see that this is a straight line. So upon inspection, we can conclude that that's true. So what you might do is sort of choose a value like here, or choose a point that's on the line right here. And then we can look at calculating the K, the constant K, the spring constant, just from the X and Y coordinates. And so to remind ourselves of Hooke's law, we say something obeys this law, Hooke's law, when, you know, this is true, when the force and the extension are proportional to each other. So this constant of proportionality should be just that, a constant. So if we choose a value like the extension is 20 centimeters and it looks like the force is 5.2, 5.3, 4, 5.5, 5.6, 5.7, 5.8, 5. So each one of these is 0.1. So it looks like at a force of 5.2 newtons, that's where we've got the extension of 20 centimeters. And as long as the units are consistent, newtons per centimeter, newtons per meter, you know, we can compare them. So we'd say over the range of extensions, you know, this coordinate here would give a certain value for K, which we can calculate. I will. 5.2 divided by 20, so that this spring has a spring constant of 0.26 newtons per centimeter. Since I'm looking at that entire range of extensions, I want to sort of find a point all the way at the top, and so I'll just use the final point. That's that 40 centimeter, and it looks like that's intersecting this line right here. That's 10.4. 3, 2, so 10.4, which, if you can't already sort of tell from the values, you know, 5.2, 20, 10.4, 40, right? We can kind of see that that's twice as much and that's twice as much. And so when we divide this, which I'll just do for good measure here, indeed, we should get the exact same constant K. And that's showing that the spring obeys Hooke's law over that entire range of extensions. We get the same constant that relates to the force and the extension. So doing using data, you can see there's the data that I've used, 5.2 and 20 centimeters, 10.4 and 40 centimeters. The other way to sort of do this might be to calculate the slope, you know, so like we could have taken the rise over the run for sort of different points, you know, like calculated the slope here, calculated the slope here using 2 points and compared them, the slope again should be 0.26 newtons per centimeter. The slope of this gives Hooke's law, and it's the same everywhere. We can kind of look at that and see. So that sort of working right there would be sort of what you'd want to show there. You could, you know, even explain that a little bit more clearly and say, you know, the ratio of force to extension for the 20 centimeter, you know, extension gives a spring constant of 0.26. The ratio of force to extension for the extension of 40 centimeters also gives a constant of 0.26. This shows that the force is proportional to the extension and therefore the spring obeys Hooke's law. So anything like that would remove any doubt from the examiner's mind that you sort of know what you're doing. And they'd award you the marks for that. Now we want to calculate the spring constant. Well, we've already done that. Well, now note that they have newtons per meter here, right? Not newtons per centimeter. So we could say, really the better way to do this would be to take the y2 minus y1 over x2 minus x1, right? Take the slope sort of that line using 2 different points. So we already sort of took the coordinates out to just sort of do a rough kind of calculation over here. So 10.4 minus 5.2 is 5.2, and 0.4 minus 0.2 is 0.2. So it's the identical calculation to this one. We just sort of, I wanted in newtons per meter, so I've converted that to meters. So I got 5.2 over 0.2, and if it's 0.26 newtons per centimeter, then it's 26 newtons per meter. And you could have converted this or sort of done like I've done. All right, so now we want to solve for the work done, extending the spring from 20 centimeters to 40 centimeters. The work done in extending the spring is equal to the energy that it possesses. So like work and energy are the same thing. We have to do work. We have to apply a force over a distance, right, to sort of store energy inside of this elastically. And so the area underneath this curve here solves it. Note that we've got this little bit of rectangular part of the graph down here, and then we've sort of got a triangle that it intersects the y-axis sort of not exactly at 5, but at 5.2, as we've already sort of seen here. So what we need to do is find the area underneath this, the work done in extending it. Let's think about this. The work done extending the spring from 20 to 40. Yeah, so it's the area underneath this curve here. And so I would split it down into a rectangle right here. That's going to be 0.2 newtons tall. So the length is 0.2 newtons from 5 to 5.2. And the width is 20 centimeters, so 0.2 meters. So this rectangular part of the graph, so I won't draw the whole thing, but that rectangle there is going to have a length times a width of 0.2 newtons times 0.2 meters. And so 0.2 times 0.2 is 0.04. And so we get a little bit of work done here, 0.04 joules or Newton meters just from this part of it. But then we've got the 1/2 base times height. And so we've got this sort of triangle here. So 1/2 the base is still 0.2 meters, right? So from 20 to 40 is 0.2 meters. But then the height of this starts at 5.2 and it goes up to, remember, 10.4. So that's the 10.4 minus 5.2, which is 5.2 newtons. So 5.2 newtons times 0.2 meters times 0.5 gives me 0.52 joules for the triangular part, and adding back in the 0.04 joules gives me a final work done of 0.56 joules. So it's the sum of those two, because we want the total area underneath. So for this one, let's report our final answer as 0.56 joules. Remember, this one was 26 newtons per meter. And then it says a force is applied to the spring to give an extension of 50 centimeters. State how you would check that the spring has not exceeded its elastic limit. Well, we know, if we know sort of what the definition of the elastic limit is, then that's sort of the point that if we do exceed it, it's not going to return to its original shape. And so we want to kind of put that in our own words to say, apply the force that gives the extension of 50 centimeters and remove the force. If the spring returns to its original shape, then it has not exceeded its elastic limit. But if the spring does not return to its original shape, then we have exceeded it. So we can kind of say, remove the force causing the 50 centimeter extension. And if the spring returns to its original length or shape, original length, then the elastic limit has not been exceeded. So we only exceed it if it doesn't return to its original shape. It's like we've overwhelmed the integrity of the spring, we've stretched it out too much, and now it'll never be the same spring again. Demonstrating that in class always requires me to sacrifice a spring. So there's a whole spring graveyard to demonstrate how we can indeed exceed the elastic limit for springs, right? Those springs will never be the same again. They don't return back to their original shape. All right, 9 marks for this one. Let's be mindful to give ourselves some feedback here. So I'm going to go to my address bar. See, I'm using the cienotes.com website. It's a great resource, and you can conveniently change QP to MS, change the question paper to the mark scheme. It will immediately queue up the appropriate one because all the rest of it is the same. This one came from May, June 2016. And we were just doing question number, should become clear in a moment, 4. The energy stored in a body due to its extension, compression, deformation, change in shape or size. So, you know, maybe we should have had the word change in there, the energy stored in an object due to a change in its shape, right? Due to its shape. So maybe the keyword change might cost us the mark there. So, and I was honestly debating that in my mind to say, should we say a change in shape, or it's stored in its shape, like some objects, you know, but it really is a change, right? Like if you have a, you know, like one of those bouncy balls that you kind of turn inside out and then you set them down and they pop up. We should have one of those things like that. Anyway, there's some elastic potential energy stored in that. You're changing it, like you have to change it first, and then it sort of tries to go back to its original shape. All right, so it says 2 values of F over X are calculated, which are the same. So that's what we did. Or the ratio of 2 forces and the ratio of the corresponding extensions are calculated are the same. That's okay. So that here they're sort of comparing the ratio of the forces. Like this force to that force is 0.5, and this extension to that extension, you know, is 0.5. You know, the ratios of the corresponding values are the same. Or the gradient of the graph is calculated, and the coordinates of one point on the line are used with a straight line equation to show that C is 0. So you could, you know, have gone about it that way. And therefore, Hooke's law is obeyed. So you have to actually answer the question which says, you know, use this data to say whether or not this thing obeys Hooke's law. And you have to actually make that statement. So you say, so yes, Hooke's law is obeyed here. And then they calculate the K, 26 joules per meter. Good. Now here it looks like we made a mistake. We didn't get 1.6, did we? We got 0.56, so that's great. So think about that. But then this one's good. Remove the force, and if the spring goes back to its original length, you know, then it would be. All right, what do we do here? Area under the graph. So it looks like they've subtracted away the 1/2 base times height from this 1/2 base times height, but here they've done the entire extension. In other words, here's maybe where we went wrong. This is really frustrating. They only showed us a piece of the graph, right? Like sort of where it's at, like from 20 to 40. But I think what we needed to do was consider, well, no, let's read the question again. So 1.6 is the answer they get. That's 3 marks right there. The work done extending the spring from 20 to 40 centimeters. So the work done extending it from 20 to 40. So if we imagine this entire graph, okay, like they said, if we did, extend this down, it's going to cross at sort of 0 here. So we can imagine there's a line like this. And with 0 newtons of force, there's 0 centimeters of extension. And eventually, once we get to, 5.2, so let's just say like 5, 10, 15, something like that. Once we get to about 5.2 newtons of force, that's where it's showing us 20 centimeters. And then once we get to 10.4 newtons of force, that's where it's showing us the 40 centimeters. It's saying, what is this area here? So you see what we did is we just sort of cut it off like this, and we weren't mindful of like all the values that go down. And so we completely, I completely disregarded all of the important sort of, physics that we sort of need here. And so I think what we have to do, what they were subtracting away was, I think, this area. All right. And yeah, so what we calculated was like the area of like this. Okay, that's what we calculated. And we're missing this whole sort of area down here. So, and it could be that, the numbers just kind of work out. So the way that I would sort of, okay, now that I've given myself feedback and I'm like, oh, I see what I've done. I've missed part of this graph. They've only shown me a piece of it. And so it might be better to, think through it like, it's the area of this trapezoid right here. Okay, so I could sort of calculate the area of this entire triangle and subtract away the area of this one. I think that's maybe what the mark scheme shows as the first one. So in other words, if I say all I care about is this area here, obviously what we did was sort of wrong. And I think what you've done is a correction to it. We say, well, if you just calculate this and add it back in, I wonder why that works there. I have to think about it. But to me, if I sort of redraw this and I go, okay, 1/2 base times height for this entire thing. So I know the height of my entire triangle is 10.4 newtons. And the base is 40 centimeters or 0.4 meters. And so this would give me all of the elastic potential energy stored in the spring. But the question doesn't ask for that. It asks for just the work done extending it from 20 to 40. So it's like, if I know the total energy is going to be this, then what I need to do is subtract away the energy it already had at 20 centimeters. And so I'm going to subtract away the 1/2. And then at 20 centimeters, we know that it was 5.2 newtons. And this is the base. So the height is 5.2 and the base is, 0.2 meters. at the 0.02, that I was just looking at this tiny little sort of triangle right here, right? So again, this is not a true zero, and I should have recognized that in the calculation. So I'm pretty sure this agrees with what they put in the mark scheme as how to calculate it. 0.5 times 10.4 times 0.4 would give us 2.08 joules. So that's all the energy stored in it. That is the elastic potential energy stored in the spring. But the work done extending it from 20 to 40 is just the sort of the energy that we added into it from here. So we got to subtract away this area, which is 1/2, base times height. And so 0.5 times 5.2 times 5.2 times 0.5 times 0.2 is 0.52. And so 2.08 minus 0.52 is 1.56 joules, which is about 1.6 joules. So that's sort of the answer you get when you solve it that way. I suppose the other way to do it would have been if you know the area of a trapezoid. It's like 1/2 base 1 plus base 2 times height, maybe something like that. This one right here. In other words, that shape right there is a trapezoid, right? And so it's got a base, it's got another base, it's got a height. And this, I think, is the formula for a trapezoid. But if it's not really familiar to you, like I'm not even too sure about it. I have to look that up to like remind myself, like what's the formula for a trapezoid? But it's a good check on our calculate. I mean, we know that's the answer. We look at the mark scheme, but this would be another way to maybe think about it. It's like, oh, if I could just measure this base, which would be the 5.2 number, this base is the 10.4 number. The height would then be the 0.2 meters. And so let's just do it real quick. It would be 0.5 times 10.4 plus 5.2 times 0.2. It does indeed give you the exact same 1.56 answer. So if you happen to memorize the formula for a trapezoid, that's another way, like triangle minus triangle equals a trapezoid, right? It's like we did just like big triangle minus the small triangle gave us the area of our trapezoid there, but there is a formula to directly calculate the area of the trapezoid, which you could also employ and get the correct answer. So the feedback for this one is look at the axes, and if there's not a true zero, don't disregard it like I did as an example of what not to do. Account for all of those sort of values underneath, even if you have to do sort of a rough sketch off to the side like this, just sort of remind yourself. So that's how you get to the correct answer on that.